So, for the remaining part of this module, we will do some worked out examples. Okay. So, these examples will help you understand the theory that we have already discussed, and also will derive some results which will be used later during the later part of the course. Okay. So, we will first start with the following example. Okay. Consider that you have a rod of initial length L0, okay, and under the action of external loads, the rod elongates and the current length of the rod is L. Okay. So, now you can define different kind of strains. Okay. Without going deeper into how these strains are actually derived at or arrived at, okay, we will just look into these 4 strain measures. So, this is a uniaxial case. So, there is no tensor or vector involved. The first definition of strain is called the injuring strain. Okay. This is the injuring strain, which is nothing but the change in length, okay, which is nothing but the final length minus the initial length divided by the initial length. Okay. So, this is like delta L by L. Okay. That is the change in length divided by initial length, that is called the injuring strain. Okay. The next strain we can define is logarithmic strain. Okay. So, this is nothing but log of final length divided by initial length. Okay. So, this strain is also called the true strain. Okay. The third strain measure, okay, is called the Green strain, okay, which is written here. Okay. The subscript is green. Okay. This is defined as the change of length square divided by 2 times of the square of the original length. Okay. And the last strain measure we have is the Alamansi strain measure. Okay. So, Alamansi strain measure defines the change in length square divided by twice of square of the final length. Okay. So, now once we have the initial rod which is extended to this final length, then what we have been asked is to find out the directional derivative of these strain measures where L is the final length and L0 is the initial length, and for a small change u in the length L. Okay. So, if there is a small change u. Okay. So, now what is the change, okay, in the each of the strain measures. Okay. What we are doing is we are changing length from L to L plus u, and we want to know what will be the change in the strain measures, okay, each of these 4 strain measures because of this much change u change in the final length of the bar. Okay. So, you would you would recall from the concept of directional derivative that the final value of the quantity, if you expand using Taylor series, will be the initial value plus the change. Okay. So, now we actually want to compute that change, which is nothing but the directional derivative. Okay. So, we will start with the first strain measure, which is the injuring strain. Okay. And then the directional derivative of the injuring strain, okay, at length L. Okay. So, the injuring strain depends on length L. Okay. L0 is fixed, it is a constant quantity. Okay, only thing that can change is L. Okay. So, the directional derivative of engineering strain at length L in the direction of change u, and the direction is here in the same direction as the length L, okay, will be given by, and you will recall from our previous discussion on how to compute the directional derivative. It is given by d by d eta, okay, d by d eta of the engineering strain evaluated at L plus eta u, okay, and then substituting eta equal to 0. Okay. So, now what we do in our definition of the engineering strain, which is over here, will substitute L by L plus eta u, okay. And then that is what we have done here. We put L as L plus eta u, that is what this expression means. Okay. We have to compute engineering strain at L plus eta u. So, we substitute L as L plus eta u, and then the usual definition of engineering strain follows: L plus eta u minus L 0 divided by L 0. Okay. Then the next thing, okay, we do is take a derivative with respect to eta, okay, with respect to eta. Okay. So, if you take derivative with respect to eta, so L does not depend on eta, okay. Obviously, there is only one eta term which is over here, and L 0 does not depend on eta. So, that also goes away. So, the only term we are left with is u, okay, because d by d eta of eta u will be u, okay, divided by L 0, and this has to be evaluated at eta equal to 0. Now, since we do not have any eta term in this expression, okay, so this eta equal to 0 does not have any meaning. Okay. So, finally, we arrive at following value of the directional derivative of the engineering strain at length L in the direction u, and this is given by u by L 0. Okay. So, this is nothing but the change in length L divided by original . Okay. So, now if L was very close to L 0, okay, if L was nearly equal to L 0, as would happen in elasticity problem, small deformation problem, then in that case the directional derivative of this engineering strain is nothing but your usual definition of strain, true strain that you take, which is change in length divided by original length. That is the true strain that you take. Okay. But this is only when you have small deformation problem, okay, where elasticity assumptions hold. Okay. So, this is the, so this final values shows the change in the value of engineering strain when you change the length from L to L plus u. Okay. So, u by L 0 will be the change in the value of engineering strain in the direction of u. Okay. So, this is the directional derivative of the engineering strain. Okay. Next, we come to what is called the logarithmic strain or the actual true strain. Okay. So, this is given by natural log of ratio of final length to initial length, okay. and to compute the directional derivative of logarithmic strain at L, length L, in the direction of u, will follow the usual procedure, which is given here. Okay. So, d epsilon log. Okay. So, logarithmic strain at L in the direction of u will be equal to d by d eta, okay, of logarithmic strain evaluated at L plus eta u, okay, and then substituting eta equal to 0. Okay. So, now in our definition of logarithmic strain, which is log of L by L 0, we will substitute L equal to L plus eta u, okay, L plus eta u, okay, divided by L 0, and then we have to take the derivative with respect to eta. Okay. So, this is nothing but d by d eta of ln L plus eta u minus ln L 0. Okay. So, the second term does not have any eta term. So, it goes away, and the derivative of first term will be u by L plus eta u evaluated at eta equal to 0. So, next thing is, once you have taken the derivative with respect to eta, you substitute eta equal to 0. Remember, eta is only an instrument for carrying out the derivative. Okay. So, unlike in engineering strain where there was no eta present, okay, here we have a term for eta. Okay. So, naturally, when you substitute eta equal to 0, the second term in the denominator goes away. Okay. It goes away, and what you actually get is u by L. Okay. So, this is the change in the value of length L divided by length L itself. Okay. Sorry, in this previous slide I said this is the true strain. Sorry, this is your u by L 0 is your usual expression for engineering strain. Okay, change in length divided by original length. Okay. And then this, in case of elasticity, this u by capital L, which is the final L, in case of elasticity, because L is very close to L 0, this is your actual definition of true strain, change in length divided by current length. Okay. Next, we go to our third strain measure, which is nothing but Green strain, and this is defined as L minus L 0 the whole square divided by twice of L 0 square. Okay. So, taking the directional derivative of the Green strain at length L in the direction u will be given by following expressions. Okay. So, the way you compute is, you substitute in the expression of Green strain L as L plus eta u. Okay. So, you substitute L as L plus eta u, okay, and then that is what you get here. Okay. L has been substituted with L plus eta u, and this minus L 0 divided by twice of L 0 square. Okay. So, once you take the derivative, what do you get? It is only the first term, okay, here has eta. Okay. So, when you take derivative with respect to eta, you will get twice of L plus eta u into u, okay, which is here. Okay. And then the second step for computing the directional derivative is you substitute eta equal to 0. Okay. So, which means the second term over here will go away, and this 2 will cancel out. Okay. So, what you are left with is u L divided by L 0 square. Okay. So, this is u by L 0, you can see this is like this L by L 0. Okay. So, now u by L0 you would recall, okay, was the directional derivative of engineering strain, and the second term is the ratio of the lengths. Okay. So, this is the UL by L0 square is the change in the value of Green strain, okay, because of a change u in the value of length L. Okay. So, once we have done this, the last strain measure that we had is called the Allemande strain measure. Okay. We will look into detail of all these strain measures once we go into kinematics. Okay. So, the Allemande strain measure is given by L minus L0 the whole square divided by twice of L square. Okay. So, to compute the directional derivative of the Allemande strain measure at length L in the direction u is d by d eta of Allemande strain measure evaluated at L plus eta u, and then substituting eta equal to 0. Okay. So, in the next step what you do, substitute L by L plus eta u in the expression for Allemande strain. Okay. So, that is what we have done here, minus L0 square divided by 2 plus L plus eta u the whole square. Okay. So, taking the derivative, okay, now you note both the numerator and the denominator have eta. Okay. So, you can take the derivative of this expression, okay, which is a standard exercise. Finally, you will get u by L0 square divided by L plus eta u the whole cube, and then you have to calculate this at eta equal to 0. So, only in the denominator you have eta. Okay. So, when you substitute eta equal to 0, you get UL0 square divided by L cube. Okay. So, this is nothing but u by L, okay, L0 by L, and this is L0 by L. Okay. So, we will come to it later, okay, when we go to multi-dimensional case. This is a 1D case, but if we go to multi-dimensional case, the same form will come, but in the multi-dimensional sense. Okay. So, I will leave it at this point. All you need to care about right now is that the change in the Allemande strain, okay, at length L in the direction u is nothing but u by L0 square divided by L cube. Okay. So, for this simple case, you can now see how we compute the directional derivative. Okay. So, next we go to computing the directional derivative where second order tensors are present. Okay. And consider this expression. Okay. So, here B is a second order tensor which depends on another second order tensor which is A, and how it depends? B is A square, which means A into A. Okay. So, once you have A into A, we can write it as A square. Okay. So, in direct notation you can write power, but when you are writing in indicial notation, I told, if you remember, that you cannot write that power. Okay. You have to break into terms of single degree. Okay. So, now we wish to compute the directional derivative of the second order tensor B, okay, in the direction of an increment u in A. Okay. What it means is, suppose I change A, the second order tensor, from A to A plus u. So, because B depends on A, therefore, there must be some change in the value of B, because I have changed A itself. Okay. So, what will be that change in the value of B, okay, at A in the direction of u. Okay. So, to do that we have to take the directional derivative, and from the concept of directional derivative, okay, so the directional derivative of b at a in the direction of u will be d by d eta of b evaluated at a plus eta u. Okay. So, this bracket over here does not mean that you have to multiply b by a. Okay. It means b is a function of a plus eta u. Okay. So, the directional derivative is d by d eta of b plus eta u, b function of a plus eta u evaluated at eta equal to 0. Okay. So, now what we do in our expression for b, we substitute instead of a, we write a plus eta u, and we do that in this second expression. Okay. So, here if you substitute a as a plus eta u, this is what you are going to get. Okay. This is the first a which is replaced by a plus eta u, this is the second a replaced by a plus eta u. Okay. So, now what we need to do is we open up the brackets and then simplify the expressions. Okay. Remember, the order of multiplication for two tensors is very important. What it means is a multiplication of two tensors a and b will not necessarily be equal to b into a. Okay. So, we have to maintain that order. Okay. So, we have to see here. So, this is the first term multiplied by these two terms. Okay. So, a into a is a square, then you have a into eta u, which gives you eta into a u. Okay. Then the second term eta into u multiplied by this first term. Okay. So, gives you eta into u a, and then the second term multiplied by the second term on the second expression gives you eta square u square. So, now you have seen we have a u and u a. Okay. I cannot write this also as u a u. Okay. It will be wrong to do it, okay, because of this property. Okay. Now, what we do? We have to take the derivative of this expression in the bracket with respect to eta. Okay. So, now you have a constant term, okay. You have a linear term in eta and you have a quadratic term in eta. Okay. Once you take the derivative, the first term goes away because there is no eta involved. The second and the third term you have eta. So, derivative with respect to eta gives you a u plus u a, and the derivative of this last term over here will be twice of eta into u square. Okay. And then we have to compute this expression at eta equal to 0. Okay. So, once you substitute eta equal to 0, this third term over here goes away because 2 times 0 into u square will give you 0, and we are left with the first two terms, and that is your answer. Okay. So, the directional derivative of tensor b, okay, at a in the direction u is nothing but a u plus u a. Okay. So, if you change a from a to a plus u, the change in b will be a u plus u a. Okay. Next, we move to a little more complicated case, okay, and we have encountered this particular expression in our previous lectures. Okay. So, we have to compute the directional derivative of this quantity q v equal to v dot a v, where a is a constant tensor, okay, constant second order tensor. Okay. So, what it means is you have this quadratic function, okay. It is a scalar value, q is a scalar value, okay, because a v will be a vector, because a second order tensor operates on a vector v to give you another vector, and then you take a dot product with the vector itself. So, finally, you will have a scalar. Okay. Now, what we want to know is, if we change the vector v from v to v plus u, okay. So, what will be the change in the value of q in the direction of u? Okay. Now, we are given that A is a constant tensor. Finally, we are also interested in evaluating the gradient of q. Okay. So, how do we calculate the gradient of q? Okay. So, the way to do is the directional derivative of q, okay, at v, okay, in the direction u will be d by d eta of q evaluated at v plus eta u, and then substituting eta equal to 0. So, this will give you the value of the directional derivative of q at v in the direction u. Okay. So, the next step is we substitute v equal to v plus eta u in our expression of q, okay, which is v dot a v. So, that is what we get, v plus eta u dot a into v plus eta u. Remember, a is a constant tensor, second order tensor. Okay. So, we can take a inside the bracket, okay, that is what we have done. Okay. So, we have v plus eta u dotted with a v plus eta a u, okay. And then we can again take the dot product of these two brackets. We can carry out this expression, simplify this expression. The first term will be v dot a v, which is here, okay. The second term will be v dot eta a u. So, eta times v dot a u. Then the next term will be eta u dotted with a v. So, eta u dot a v, okay, plus eta square u dot a u, okay. Sorry, there is one more plus, okay, eta square u dot a u, okay. Now, we have to take the derivative with respect to eta, okay. So, our first term over here, okay, does not have any eta. We have a linear term in eta and we have a quadratic term in eta. But before that we proceed further, we can see we have v dot a u here and we have u dot a v here, okay. So, we can bring v on this side and u on this side, okay, by following procedure, okay. That will be easier for us to understand and later on to compute the gradient, okay. So, how I have written u dot a v, okay. So, the way I have to write is, I can write initial notation, this is u I and a v I, okay, because a is a vector, okay. So, u I a v I. Now, this is u I a I j v j, okay. So, this I can write as v j a I j u I. This I can write as v j a transpose a j I u I. Okay. Okay. Once we swap the indices, I have to put a transpose. Okay. So, now this I can write V j A transpose u j. Okay. And then equivalently I can write in direct notation A transpose. Okay. So, that is how u dot A v is same as v dot A transpose u, and this is what we use here to write u dot A v as v dot A transpose u. Okay. Now, we have v everywhere, we have v, okay, and we have u here. Okay. So, we have v at the first position. Now, we take derivative with respect to eta. Okay. So, the first term goes away, this term will be v dot A u plus v dot A transpose u plus 2 eta u dot A u. Okay. And then we substitute eta equal to 0, which means this term, this last term goes to 0, and we are left with v dot A u plus v dot A transpose u. Okay. So, if you change v to v plus u, so the change in q will be v dot A u plus v dot A transpose u. Okay. So, you can very clearly see it was a nonlinear expression. So, you just changed v to v plus u, but this change over here which we get in the value of q is not very clear at the very start unless until we have computed the directional derivative explicitly. Okay. So, this is the directional derivative. Now, we have been asked to compute the gradient. Okay. So, to compute the gradient, okay, we note that the gradient of q, okay, with respect to v, okay, gradient of q at v in the direction u, okay, this is nothing but your directional derivative, is nothing but v dot A u plus v dot A transpose u. Okay. And then our directional derivative is also equal to gradient of q dot u, and because A dot b is same as b dot A, I can write this as u dot gradient of q. Okay. So, I can substitute this on the left hand side and I will get, okay, and then I will get u dot gradient of q will be equal to u dot A transpose v plus u dot A v. Okay, remember. So, what I have done over here is I have shifted u from the right hand side to the left hand side. Okay. So, over here if I shift u here and v here, I will get a transpose on A. If I get u here and v here, I will get a transpose of this transpose, which is nothing but the tensor itself. Okay. So, I will have u dot A transpose v plus u dot A v. Okay. And then I can take out u from the left hand side and I can write A transpose v plus A. Okay. And now I can compare the left hand side to the right hand side. So, you have u dot gradient of q, and on the right hand side you have u dot this particular expression in the bracket. Okay. Therefore, the gradient of q, okay, is nothing but A transpose v plus A v. Okay. That is how you compute the gradient of this scalar function q. Okay.